In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
The biggest things in space are gargantuan beasts. Each one is a heavyweight in its galactic division.
The universe is an unimaginably large place. It's so big, it's really hard for human beings to actually comprehend things of these size scales.
On Earth and in the universe, size matters, but it matters in different ways.
In space, bigger is not necessarily better. And oftentimes, the winners live large and die young. They're the Mount Everests of the cosmos. Astronomers aim their telescopes at them like paparazzi, eager to capture images of their every movement. They are the biggest things in the universe, and their sizes are truly mind-boggling.
The good thing about being huge in the universe is that the universe is even huger than you are. So there's plenty of space to stretch out and get your size measured among intelligent civilizations that are having a look.
The first thing you find out when you start studying astronomy is how darn big everything is. Almost everything you're studying is so far beyond any kind of human scale that we're ever going to encounter in our normal lives.
The universe is brimming with gigantic objects. Within our own solar system, Earth is the 5th biggest planet. But it's 100 million billion times smaller than the largest stuff in space. So what holds the coveted title as the biggest thing in the universe? Most astronomers agree it's the cosmic web, an endless scaffolding of superclusters of galaxies surrounded by dark matter, an invisible and mysterious form of matter that accounts for 90% of the universe's mass.
The largest thing in the universe, you might even wonder if it's a thing at all. It's a web of dark matter that fills the volume of the universe. Dark matter is this matter that we can't even see. It doesn't emit any light, but it is filled throughout the universe, and there's structure in it.
Dark matter is something much more mysterious than most people know. Literally, the stuff that makes me up. Dark matter isn't made of that. I don't think you could smell it. I don't think you could touch it. It simply has gravitational attraction.
The cosmic web of dark matter becomes visible when looking at the objects that fill it.
This cosmic web really is almost like a three-dimensional spider's web. At the very center of all the vortexes, there are the superclusters, clusters of thousands of galaxies. And then filaments of galaxies connect them all the way across the volume of the universe.
The deepest, strongest gravity at the intersections of these web-like structures is where all the gas falls. And that's where galaxies form, clusters of galaxies form.
But just how big is the cosmic web?
If the Milky Way galaxy were the size of a poppy seed, then the observable universe, everything we can see, would be about the volume of the Rose Bowl Stadium. Now that entire volume is filled with the cosmic web, superclusters linked together from one side of the universe to the other.
The origins of the cosmic web remain uncertain, but scientists think its initial seeds were planted in the Big Bang, the beginning of the universe.
During the Big Bang explosion, the whole universe blew up essentially and expanded very rapidly. So the cosmic matter web contains all of the original matter that was created during the Big Bang just blown up into the very, very large structures that we see today.
Scientists are actively trying to map out the cosmic web, which spans the entire universe.
One way is to look at hot X-ray emitting gas and how it's contained by the gravity present in the dark matter. Another way is to look at something called gravitational lensing, where light is bent by the gravity of the cosmic web. And so we're able to sort of see the outlines of that cosmic web by the way it distorts the light that's behind it.
The cosmic web basically contains everything in the universe. But some scientists question whether it's technically the largest object, because the web isn't continuously connected throughout space.
The cosmic matter web is not actually the largest gravitationally bound object in the universe. Because all the matter in the universe has expanded so vastly, the force of gravity is not enough to keep it together in one area, whereas superclusters of galaxies are actually gravitationally bound, meaning that they have enough mass to produce enough gravity to hold them together over the passage of time.
Astronomers don't have a firm estimate, but the cosmic web could be made up of hundreds of thousands of supercluster complexes. These are mega collections of galaxies, gravitationally bound, up to hundreds of millions of light years across.
The universe is organized hierarchically. Stars make up galaxies, galaxies make up clusters, clusters make up superclusters. You could draw an analogy that a cluster might be the North American continent, and a supercluster might be the association of cities on the North American continent, cities on the European continent, cities on the Asian continent, etc.
The current record holder for the largest supercluster of galaxies is called the Shapley Supercluster. This dense region of galaxies is 400 million light-years long. So it would take the fastest interplanetary spacecraft trillions of years to travel across it. The Shapley Supercluster spans several constellations and is almost 650 million light-years from our Milky Way galaxy.
I have here a small toy boat, which is a replica of the Queen Mary, which you can see here behind me. And this little toy is about 4,000 times smaller than the real Queen Mary. If you could just imagine that our own Milky Way galaxy that we live in is the same size as this toy boat, then one of the most massive superclusters that we know about, the Shapley Supercluster, would be the same size as the Queen Mary. So this Shapley Supercluster would be about 4,000 times larger than our own Milky Way. It's one of the most massive things we know about in the entire universe.
Astronomers have known about superclusters since the 1950s, but now they've determined their origin through recent measurements of the cosmic microwave background, which is actual radiation left over from the Big Bang. It's been concluded that all superclusters, including the Shapley Supercluster, originated during the formation of the universe over 13 billion years ago.
As the universe evolves and expands, gravity is an attractive force, so any region that has a little extra density there attracts more matter and more matter. So Shapley is a cluster that basically had the accumulation of many other little galaxies falling into it, and that's how it's gotten so big over time.
Incredibly, scientists think the Shapley Supercluster may be even bigger than it appears.
In fact, we may only be seeing a small fraction of what's really contained within the Shapley Supercluster. When the Wide Field Infrared Survey Explorer launches, we should be able to see about 10 times farther away, and hopefully we'll be able to see the rest of the Shapley Supercluster to see if it is even more massive than what we already know about.
Superclusters of galaxies will stay together over time because they're gravitationally bound.
Gravity is holding them together, so even though the universe is expanding, over time, those superclusters of galaxies will stay together, and they'll always keep orbiting each other.
We humans also live in a supercluster complex, but it's less than half the size and about 10 times less massive than the Shapley supercluster.
Our Milky Way is part of a small little cluster called the Local Group, which is part of a larger cluster called the Virgo cluster, sort of on the outskirts of that. So it's like your home address. You live on this street in this town, in this state, in this country. Similarly, the Milky Way has its larger and larger associations of which it's a part.
Superclusters of galaxies are the most crowded neighborhoods in space, but they surround equally big regions where almost nothing exists. These bare spots are called voids.
Voids are the opposite of clusters. If clusters are where all the galaxies are, voids are where all the galaxies aren't. And you do see this kind of frothy web-like structure of clusters and voids and clusters and voids. So it's kind of like cities and countryside, cities and countryside.
The largest confirmed void in the universe remains Boötes. Named after the constellation where it resides, this near-empty space is a whopping 250 million light-years across. That's equal to 2,500 Milky Way galaxies placed side by side.
Look out into the cosmos in any direction, and you'll see something. You'll see stuff. You'll see galaxies. You'll see gas, dust. You'll detect dark matter. Everywhere you look, there's something. Yet here's this giant hole with nothing in it.
The Boötes void, which was discovered in 1981, is almost completely devoid of galaxies. A new way to search for even larger voids may be possible by precise measurements of the temperatures of the cosmic microwave background radiation. Subtle cold spots in this radiation could locate the directions of large distant voids.
The story of their formation is basically the reverse of how superclusters form. The voids must have started out in the first microsecond of the Big Bang as slightly low-density regions. But with time, they became less and less dense. All of the matter flowed away into the sheets and filaments, leaving the voids emptier and emptier of matter until today there's almost nothing but a few little dwarf galaxies in some of these voids.
Voids and superclusters are just some of the big things contained in the even larger structure called the cosmic web. But the web also holds other immense objects, including colossal bubbles that might hold missing clues to the formation of galaxies. The universe is packed with monstrous things. Researchers have recently discovered giant clouds of gas that resemble something out of a horror movie. These mysterious objects are called Lyman alpha blobs.
My personal favorite biggest objects in the universe are the Lyman alpha blobs. An unpredicted, unexpected phenomenon where you're catching a galaxy in the first phases of its formation and collapse. A Lyman alpha blob is very much like this expanding soap bubble. Except in the case of the soap bubble, it's the air which is making it fill up. A Lyman alpha blob is expanding because of heat. A lot of energy has been injected into this gas to make it heat up. And when you put all that energy into a gas, it inevitably tends to puff up and expand exactly like an expanding bubble. In the case of a Lyman alpha blob, it's being puffed up by heat and maybe also by the ultraviolet radiation from the newly formed stars.
The largest known Lyman alpha blob is a colossal amoeba-shaped structure that resembles a giant green jellyfish. It's 200 million light-years wide and is located in the constellation Aquarius.
When we're looking at the Lyman alpha blob, we're seeing gas that's sort of spread amongst these very first stars and galaxies. It's kind of an amorphous shape of about 30 separate little blobs inside of it. It's very large and very massive. The whole structure is about 3,000 times the size of our own Milky Way galaxy.
The Keck and Subaru telescopes in Hawaii contain special filters that are able to see this faraway blob, which spreads out along curvy tentacles. Scientists estimate that the largest Lyman alpha blob was formed about 12 billion years ago, almost 2 billion years after the Big Bang.
The observational technique we use to see that gas, it refers to a very specific color of light, emission of light that's called Lyman alpha. So you hear a phrase Lyman alpha blob because if you take an image of the sky through a filter that gives you only that Lyman alpha light, that very special wavelength of light, you'll see a little blob on the sky.
Lyman alpha blobs are perhaps precursors to the galaxy clusters we see today. Within these gigantic bubbles may exist cocoons that will one day spawn new galaxies.
The Lyman alpha blobs are probably a fairly special, short-lived phase in the evolution to creating a galaxy. I expect that most of them are going to collapse and form young galaxies in the next 100 million years or so of their lives. So it's a special phase just when a galaxy is beginning to pull itself together. The search of the universe for Lyman alpha blobs is just beginning. We'll undoubtedly find many more of them, and even perhaps some larger ones in the future. Stay tuned.
Lyman alpha blobs may hold the answers to the formation of individual galaxies, which are gravitationally bound systems containing stars, gas, dust, and dark matter. At least 100 billion single galaxies exist in the observable universe. They range in size from 10,000 to millions of light years across.
Galaxies, these titanic collections of stars, I think of them as cities, having been born in one myself. Not only a galaxy, but also an actual city. A native of New York, where everyone is crowded together. Galaxies are sort of how matter has organized itself in the universe.
In the competition for largest single galaxy in the universe, sizing up a winner is challenging.
The problem in saying what's the largest galaxy is in deciding where they end. Galaxy does not have a sharp edge, it just gets thinner and thinner as you go further out. It's exactly analogous to saying where's the end of a very large metropolitan area. Where's the end of Los Angeles? You can go out 50 miles and you'll still find a fairly high density of suburbs. The suburbs of a big galaxy like the Milky Way extend out very, very far, more than 100,000 light years. And with a giant galaxy, those suburbs extend out hundreds of thousands of light years.
Since scientists can't determine a clear winner, several galaxies share the title as biggest. They're called cluster diffuse, or CD galaxies, and they sit in the centers of rich clusters of galaxies.
If you think about the cosmic web as being sort of like a three-dimensional spider web, well, then the spiders lurking in the middle of the web are these monstrous CD galaxies, as we call them. These galaxies can have masses that are, in some cases, maybe 10 times or 20 times the mass of our own Milky Way.
These CD galaxies are the largest galaxies in the universe. For example, IC 1101 sits in the center of a galaxy cluster called Abell 2029, and it's 6 million light years across. Compare that to our own Milky Way, that's 100,000 light years across. It's a really big galaxy. It's 60 times the size of our Milky Way.
CD galaxies are elliptically shaped, as opposed to a disk structure like our Milky Way. This is because they've achieved their size by bulking up on other galaxies through galaxy mergers.
You may have heard the phrase galaxy cannibalism, where one galaxy eats another. That goes on all the time in clusters of galaxies. So sitting usually down at the very center of a massive cluster, you'll find one big galaxy.
These CD galaxies have so much mass that they are the 800-pound gorilla wherever they are. You see little galaxies maybe orbiting around them, but basically it's eaten up everything nearby.
The largest galaxies may be 6 to 20 million light years across. However, there are other objects even larger. They're called radiolobes. Stretching out from both sides of a galaxy, these immense structures are actually hurling jets of charged particles that emit radio waves.
So we're here in this auto body shop where I'm going to use these two torches to simulate radio jets coming out of opposite sides of an accretion disk swirling around a supermassive black hole. So in the visible, you see a small blue flame coming off of the torch. But in the infrared, you can see that the heat from the torch extends much, much further out. Similarly, with the radio jets, what you see in the optical is actually quite different from what you see in radio waves.
A typical lobe might be 160,000 light years as the lobe spreads out on both sides of the galaxy. That's about twice the size of the Milky Way galaxy's disk.
Astronomers think radiolobes are powered by supermassive black holes located in quasars. These are the luminous centers of most active galaxies.
The jets of radio energy that come from a giant black hole and make these enormous radiolobe structures are very closely related to quasars. In fact, in some cases, you can see a low-power quasar in the center of the galaxy, and then it's surrounded by these giant lobes to either side. They've been blasted out by very high-energy jets of electrons that are basically moving at almost the speed of light. And they are blasted out probably from the north and south poles of a spinning black hole.
The radiolobes depend on matter going down the black hole. As matter goes down the black hole, some of it gets accelerated up into these lobes. So the size of the lobes has something to do with the history of how much matter the black hole is actually fed on. And so over time, they'll change size.
Radio telescopes have surveyed the universe and determined the largest known radiolobe. The undeniable record holder is located in the galaxy named 3C236, which is in the constellation Leo Minor. Its jets span 40 million light years across. Scientists don't understand why some active galaxies form these jets and others don't. But one thing's certain, radiolobes will not last forever. Perhaps for only a few million years.
So just as this torch will eventually run out of gas and shut itself off, the jets from a radio galaxy will eventually die as well. When the black hole has consumed all of the material in its immediate vicinity, there'll be nothing left of the accretion disk to get shot out along the magnetic field lines, and the jet will die.
If black holes are the producers of these gigantic radiolobes, then what is the largest black hole in the universe? Scientists are currently placing bets on the winner. When it comes to the biggest things in the universe, some black holes earn a place in the record books. A black hole is a region of space where the pull of gravity is so immense that nothing can escape it, not even light. There are billions upon billions of these black monsters prowling the universe. They come in two size categories. Most of them are the stellar mass black holes, which are about 5 to 100 times the mass of our sun. And then there are the supermassive black holes that are millions to billions of times the mass of the sun.
We have the supermassive black holes, the kind that we seem to be finding in the centers of every galaxy where we've had the resources to look. HAVOC is wrought upon your environment if you're a star orbiting close to one of these supermassive black holes in the centers of these galaxies.
Black holes are not physically large regions, but when measuring their mass, they become top competitors in the galactic heavyweight division.
The center of our Milky Way, we know that there's a black hole that's about maybe 3 million times the mass of our own sun. And yet, because black holes are so incredibly dense, the actual size of the black hole is still fairly small, but incredibly, incredibly powerful gravitationally.
As their name suggests, these black beasts are essentially black because no light can escape them. So one can only be observed when its gravity affects something else in space, such as a passing star, or when it's gorging on matter around it. So, what is the reigning black hole champion?
The current record holder for the largest black hole appears to be in the incredibly luminous quasar, which has the prosaic-sounding name HS 1946 plus 7658. Why do I say it's the largest black hole? Because we know it is the most luminous quasar in the universe that's been found so far. The black hole that's holding it together, that's producing the energy, needs to be about 10 billion times the mass of the sun. That corresponds to a black hole which is larger than our entire solar system. In fact, it's just out there to remind us how bizarre a seemingly simple force like gravity can actually be.
The largest supermassive black hole wields power in the center of a galaxy. But there are other big luminous objects in the universe. In fact, there are some that seem to exist everywhere we look. When we glance into the nighttime sky, we see stars, twinkling dots of light that are actually luminous balls of plasma. Although they may seem small from Earth, stars come in a variety of sizes. From red dwarfs, which are about 1/12 the mass of our sun, to blue-white supergiants that can get as big as 150 solar masses. Our Milky Way holds 100 billion stars, including our sun, which is over 300,000 times the mass of planet Earth. And this cosmic beacon is a literal powerhouse in our solar system.
This natural gas power plant produces about 300 megawatts of power. Now that's enough to power a few 100,000 homes, but that's only a tiny fraction of our sun's energy output. The sun's power is about 2 billion times the amount of this plant. So even in spite of its distance, the sun is able to warm our entire planet.
Even so, our sun isn't the largest or the most powerful star by a long shot.
The most powerful stars are about 1 million times as powerful as the sun. So if you wanted to compare that with the Hoover Dam, you would need 30 million Hoover Dams per person on the planet to generate that much power. There's really no human scale to imagine this power output.
The largest and most powerful stars that produce this kind of energy are called red hypergiants.
That's a class of stars that's even larger than supergiant stars. So typically stars, like our sun, are fusing hydrogen into helium to make their energy. But hypergiant stars have already exhausted all the hydrogen in their core, and they're fusing hydrogen into helium in the outskirts around the core, and that makes them extremely hot and energetic, and all that energy causes the star to swell up. And so the star ends up with a very large surface area. Surface areas of the size of the Earth's orbit or even bigger.
Within the hefty field of red hypergiants, VY Canis Majoris appears to have the largest diameter. It's 2,000 times wider than our sun, and consequently, it would take the world's fastest race car 2,600 years to circle it once. This stellar champ lives about 5,000 light years from Earth, in the constellation Canis Majoris.
If you replace the sun with VY Canis Majoris, if you put this hypergiant star where the sun is, its radius would extend out past Saturn's orbit. It'd be about 9 times as far from the sun as the Earth is. So this is a much broader in diameter star than our sun is.
Astronomers determine the radius of such a large star by looking at its temperature.
We use measurements of the temperature of the star's surface, which we can get from the color of the star, and then we will also measure the total power output or luminosity of the star. And by combining those, we can determine what the total surface area is of the star, and from that we get its diameter.
Now, that assumes that you can measure its luminosity fairly well and that you know something about its temperature from its color. Most of the time, they just simply appear as pinpoints of light, and it's impossible to actually resolve it. Although there are new instruments now called interferometers, which are capable of resolving even very tiny point sources, like stars. And in some cases, there have been direct measurements of stellar diameters.
VY Canis Majoris will not be a title holder forever. The red hypergiant is losing mass at the rate of almost 30 Earth masses or more per year.
The largest stars in the universe, like VY Canis Majoris, are actually dying stars. That as stars begin to die, they burn their nuclear fuel much less stably. They puff out over time.
VY Canis Majoris is probably only a few million years old. Stars that are as massive as it is don't live very long. They use their fuel up at prodigious rates. Then they swell up into this hypergiant state and only live there for a few 100,000 years, a very short time scale, and then rapidly explode.
VY Canis Majoris might have the largest diameter, but when it comes to possessing the most mass, there's another star that tips the scale. In the wide world of stars, there are many contenders vying for the title as the largest in the universe. But when it comes to stars, big can mean two different things.
When you talk about the biggest star, you could mean one of two things. You could either mean the star that has the largest diameter, or you might mean what its mass is. And mass is a measure of how much stuff you have. It's sort of like your weight when you step on a scale, how much matter your body is made of.
According to some astronomers, the most massive star is located in our Milky Way galaxy. It's part of a binary star system known as A1, which is actually two stars that orbit each other once every 4 days.
We find there that one of the stars appears to have a mass of about 115 times the mass of the sun, and the other star is also enormous, about 84 times the mass of the sun. So both stars in this binary are among the most massive stars that we have ever measured. There may be more massive stars than the combination in A1 in this star cluster, but that's the most massive that we've been able to measure directly.
These massive stars will live full but short lives.
Massive stars are hugely luminous. Sometimes they can outshine millions of stars in their neighborhood, but at a cost. Cost is they will run out of fuel faster than everybody else. And when they die spectacularly. They explode their guts and scatter it across the galaxy. So, the cost of living a high mass life, a high luminous life, the cost of living in the fast lane is that you explode at the end of your life.
A bright star may burn out faster and die sooner, but at the same time, those hot stars are cooking up elements that are essential for life. So without really massive stars, we wouldn't be here because you wouldn't get the iron in my blood and the calcium in my bones. All of those things are formed only in the most massive stars.
We humans need essential elements from massive stars. But we also need a planet with a firm surface to stand on. Planets come in two size groups, large gas giants like Jupiter and small rocky terrestrials such as Earth. In our own solar system, Jupiter is the largest planet, while Earth trails in 5th place. Yet even though Jupiter reigns supreme in our galactic zip code, it's not the biggest planet in the universe. The largest planet with a well-known radius is called TRES-4. It's named after the Transatlantic Exoplanet Survey that discovered it in the constellation Hercules in 2006.
TRES-4 is unusually large for its mass. We can actually directly measure its radius, and this particular planet has an unusually large radius. It's about 70% bigger than Jupiter, yet it has only about 80% of Jupiter's mass. That's about the same density as cork or even whipped cream.
If you look at Earth, it's a rocky planet, very dense. And then even the gas giant planets like Jupiter are compressed gas and water and other chemicals, very tightly compressed. This thing, TRES-4, is like a marshmallow.
Although TRES-4 is light for its size, it's about 18 times larger than Earth. Scientists aren't exactly sure how TRES-4 got so large. One theory is that the planet's extremely close distance to its parent star is cooking up a lot of chemicals in its atmosphere, which is trapping heat, much like greenhouse gases.
This particular planet is only about 5% of the Earth-Sun distance from its parent star, so it's very, very close. In fact, so close, it orbits its star every 3.5 days. So you can imagine how hot and how just blasted with sunlight this thing must be. Because the planet can't cool off, it can't shrink. Because when it's very hot, when gases are very hot, they expand. So this might be contributing to keeping the radius of this planet so very large.
TRES-4 may be a puffed-up planet, but when it comes to sustaining life, bigger planets don't offer prime real estate.
These giant planets really are just gas. There's no solid structure to them at all. There's nowhere to stand on them. So it's not a very likely place to find life, because life would have to continually be blown around in the atmosphere. And that's a hard thing to evolve from.
This planet would not be a very habitable place because it's so close to its parent star. It's getting blasted with radiation from its sun. So it would be a very hot and unpleasant place to be, at least for humans.
TRES-4 currently has the largest known radius. However, the planet could be bumped out of first place in the near future.
Scientists are finding new planets basically every day almost at this point. So it's quite possible that we will find another one that's even bigger than this particular planet anytime.
In addition to planets, scientists are also discovering new asteroids all the time. These are rocky bodies that didn't become planets. And the largest one may exist in our galactic neighborhood. In our own solar system, billions upon billions of leftover rocks that didn't become planets take refuge in the asteroid belt. Some are as small as grains of dust, and others are the size of nations. Ceres was the first asteroid ever discovered, and it remains the largest known asteroid to date. Named after the Roman goddess of plants and harvest, Ceres is about 600 miles in diameter, so it's almost as large as the state of California.
Ceres is so big that it contains 25% of all the mass in the asteroid belt. Ceres is so big that if you took all the other asteroids in the asteroid belt and glued them all together, they'd only be about 2 or 3 times bigger than Ceres.
Ceres' size sets it apart from the rest of the rocks in the asteroid belt. It would take the Apollo lunar rover 10 days to drive around the asteroid at 8 miles per hour. But in addition to its size, its other distinct feature is its round shape.
You have all these Idaho potatoes orbiting in the asteroid belt of the solar system, most of which are craggy chunks of rock. Ceres is large enough, massive enough, that its gravity has overcome the strength of the rocks that contain it. And anytime that happens, the shape becomes a sphere.
Because of its round shape, Ceres now holds a dual title.
The current definition of a dwarf planet is something that in fact is massive enough and has enough self-gravity to form itself into a round shape. And in fact, since Ceres is round, we also call it, in addition to being an asteroid, a dwarf planet. We know only a little bit about the composition of Ceres right now. We know that it's made primarily of rock, but it may also have water ice, and in fact it could have clay inside it as well. The Dawn mission is actually going to go to Ceres and enter into orbit around it, and they'll bring a whole suite of instruments to bear on it, so we should learn a lot more about the composition of this unusually large asteroid in our own solar system.
Ceres may be the largest asteroid in our solar system, but it's a big universe out there.
It's quite possible that as we go on to exploring other solar systems outside of our own, that we may in fact someday find an asteroid larger than Ceres.
Our solar system contains some oversized objects. The largest planet, Jupiter, has the biggest moon, named Ganymede. Planet Mars actually contains the largest volcano, called Olympus Mons.
It's 17 miles tall, which makes it about 3 times taller than the biggest volcano we have on Earth. It's so tall that if you stood at the base of Olympus Mons, you wouldn't be able to see the top due to the curvature of Mars itself. So in our own solar system, the biggest things definitely have had a powerful shaping effect on the universe.
One might guess that the Sun would take top honors as the largest thing in our cosmic suburb. It's 1,000 times more massive than Jupiter. But is there something bigger?
The largest object associated with our solar system is the Oort cloud. And this is a very diffuse cloud of comets that literally extends about halfway out to the nearest star, Alpha Centauri. Alpha Centauri is about 4 light years away.
Astronomers estimate it would take the space shuttle hundreds of thousands of years to travel around the outer edge of the Oort cloud.
The Oort cloud is so dark and so distant that we really can't directly observe it. But what we do know is that comets come in from every direction on the sky. So there must be a spherical cloud of comets far away from us.
The origins of the Oort cloud remain puzzling. One theory is that it was formed early in our solar system. As comets fell in towards the forming sun, they were ejected into long orbits. Over time, their orbits threw them out into a giant cloud.
It's very far away, and it's filled with icy remnants that have just been left in basically the same state that they were from right around the time when our solar system formed, about 4.5 billion years ago. So they are, you could say, the archaeological remnants of the formation of our solar system.
The universe is comprised of things both big and small. But it's the large structures in space that challenge our understanding of how the universe works. Although astronomers have found many substantial objects, the quest to find even larger ones continues.
Astronomers are hoping to find new large planets, new huge superclusters, and learn more about the things that we've already seen. As technology improves with better telescopes, better detectors, newer surveys, we will be able to see farther into space and therefore hopefully discover even bigger things than we already know about.